Hello, everyone, and welcome today. We're here to talk with Skander Hannachi about AI ops, machine learning ops. Skander is a machine learning specialist. He works on Google Cloud's computer engineering team. He's based out of Seattle, Washington, and he's going to walk through some of his perspectives and experience. Welcome, Skander.
Thanks, Dave. I'll share my screen. So, good morning, good day, good evening, wherever you are, everyone. My name is Skander Hannachi. I am an AI ML specialist and solutions architect with Google Cloud's customer engineering team. I'm based out of Seattle, and I am going to talk about MLOps, machine learning operations, from a business perspective. The agenda for today will be a brief definition of MLOps, how it fits in the data science and in the machine learning landscape, and why it's important. The basics of MLOps, I won't get too technical. I'll just go a little bit into enough detail to explain why it would be relevant from a business perspective, or how it is relevant from a business perspective as opposed to an engineering one. Then I'll go into some of the business aspects that need to be considered when looking at ML ops, and then a few points to ponder on where the future direction of ML ops is. So a little bit about myself. I am an AI ML specialist with Google Cloud's customer engineering team. My day job involves interacting with Google Cloud's customers and trying to understand their business needs and whether Google Cloud can help them, how Google Cloud can better help them meet those business needs, and then going a little bit deeper than just understanding that and actually building custom solutions, machine learning architectures and models for them, and then also taking that feedback to Google Cloud's product teams so that they can improve Google Cloud's product offerings to better meet those needs. Before joining Google, I was a data scientist and machine learning architect at Nordstrom, which is a major fashion retailer in the US and in Canada. And before that, I was a retail analytics and demand forecasting consulting. I worked on demand forecasting and retail merchandising and inventory optimization problems. And before that, I was an academic. I did research. I have a PhD in machine learning. I studied machine learning meets quantum computing, but I also worked a lot on the data science applied to marine biology, where I did analysis of sonar images, forecasting fish populations and their population dynamics, and so on. And my undergraduate training was as instrumentation engineering, which is a kind of offshoot of electrical engineering, so to speak. So what is MLOps? Well, MLOps is what I like to think of as a compound buzzword. ML, machine learning, has obviously been something that has been talked about a lot over the last few years. It ties in closely with data science and AI, artificial intelligence. I'm not going to dwell too much on machine learning. I will go into ops, however. Ops is short for operations, and it became using ops instead of the word operations. I personally noticed it around 2013, 2014, that operations teams suddenly became DevOps teams. And what was that shift about? That shift about was there used to be a very clear separation between the developer, the software developer, and then the operations team, which essentially did things like tech support and making sure that the systems that were already in place in production were running. And then we realized that as a community, as an industry, we realized that separating development from ops was very inefficient, because oftentimes whenever you're trying to make sure that a software system is running in production, or that there are bugs that are being reported by the users, or there are concerns that are being raised by the business, you're going to have to involve the developers anyway. So instead of having this very neat boundary between development on one hand and operations on the other hand, have the boundary to be a little bit more fluid. Have the developers participate in the operations on-call rotation. Have the operations people give feedback back to the developers. This led to something called continuous development, continuous improvement, or continuous improvement and continuous development, CI/CD. So it was a shift in mindset as much as it was a shift in technical tools. It did happen to correspond, however, with increasing adoption of cloud technologies and cloud native technologies. So the concepts became increasingly intertwined. And then from there, ops kind of took on a life on its own, and people started talking about biz ops. I worked a lot with demand forecasting, and noticing increasingly people were using the word demand ops. There's now data ops, merch ops, AI ops, although frankly, the difference between AI ops and machine learning ops, MLOps, is not really that significant in my opinion. So people started throwing the word ops around and adding it, and it's for good reason, right? It's not really like just a empty buzzword. It is, however, significant of a change in mindset as much as it is indicative of a change in tool set. Closely related to MLOps is yet another buzzword, and hence it's a really compound buzzword, are the concepts of Kubernetes and containers, as so interestingly illustrated here by the Scott Adam comic from Dilbert. Kubernetes and containers is a technology which makes it really easy to spin up high compute and high memory resources in cloud environments on demand without having to be a fully fledged cloud engineer yourself. And this ties in very closely with MLOps. I'll go into a little bit into the details, but not too much later. As I said, this is mostly focused on the business side. But MLOps in general, keep this in mind, is closely related to the ability to containerize apps and to run them on Kubernetes. So let's review the basics of machine learning modeling as it happens on a typical data science project. You have labeled historical data. You feed that into an ML algorithm. At the end result of that process is a trained algorithm. You take that you use the algorithm to train a model. The end result of that is a trained model, which then you use to generate predictions on new data. So typical example, you train, and from my past life, is you train a model on historical sales data. You get a trained model, deploy that to production, and now new sales data comes in, and you generate forecasts on how much sales you're going to do next month. And then from those forecasts, you make decisions about the inventory that you're going to deploy. Now, anybody who's actually dealt with ML in a real business environment as opposed to an academic environment or a training context, like or a Kaggle competition or something like that, in a real enterprise production environment, and many of you who might have already seen this diagram, the actual modeling is about 10% of the effort. The rest is all about collecting the data, ensuring that the data is in the right place, ensuring that the model can predict its scale so that it can scale to thousands or tens of thousands of predictions as needed, tracking the performance of the model, all the automation, and it ends up being a little bit kind of a disillusionment of sorts for data scientists who spend all of their training and all of their learning process focusing on the red square here, and then they actually go to apply this knowledge in a work environment, and they realize that they have to spend most of their time on the blue squares instead. And so it's from this that the discipline of MLOps emerged. And to explain a little bit what MLOps is, the actual modeling process from 2 slides ago, where, okay, here's historical data, now use an algorithm to train a model, get a model, now start generating predictions from it, corresponds roughly to what we call data science, what a data scientist does. Data engineering involves the process of collecting that data, putting it the right place, and making sure that it's available in a pertinent fashion, in a timely fashion for the purposes of the business problem. And then the pure software engineering part is about, can you scale this inference process, and can you connect it to the rest of your enterprise software ecosystem. The intersection of all these three is what MLOps consists of. Here's a slightly different angle and maybe a little bit easier to grasp. You have machine learning, which is roughly what a data scientist in collaboration with a data engineer will do. You have development, which is then taking that and turning it into usable software. And then you have operations, which is having that software now it's running in production, it's generating predictions. You monitor how close are those predictions to reality? Are the in a typical, back to my demand forecasting example, in a typical week in the life of a demand forecasting analyst, they're constantly looking at how well the forecasts are doing compared to what the actual sales are, the reality, the ground truth. So how do you monitor that? How do you capture that signal? How do you create a feedback loop that goes back to the data scientists and the data engineers so that they improve their models? So now I'm going to go a little bit into the basics of MLOps. Now, that original slide where I go through what does a basic data science process looks like? Well, you're going to do exploratory data analysis. You're going to look at your data, try to understand the statistics, the distributions. That's going to be the first step into deciding how to prepare the data, how to do feature engineering, and then what type of model to use. And you develop a model, you evaluate it. You might do this a few times, iterate through it manually. At the end of this, you get a model that you're happy with. And then you take that trained model and you put it somewhere, save it. It can be, code repo, GitHub code repo. You probably want to put it in some sort of persistent storage bucket, just like store the actual model artifact, not just the code. And then you hand it over to an engineer to deploy it. This is where a lot of people are today, where I would say the industry has progressed a little, but some people are still here. But this approach to doing machine learning and data science was state of the art circa 2012, 2013. This doesn't scale. It is very difficult to do this frequently, and more importantly, it's very difficult to do this in a reproducible fashion. Let's say, you have one data scientist and they switch roles, they go to another part of the organization, or they leave the organization altogether. Then the steps that I showed in the previous slide, the next data scientist will have to go through all of that again, and it's very hard to kind of keep track of what the previous person did. This is one issue, one challenge that you might face. It's also difficult to do this when you have dozens, even hundreds of models. This can happen, for example, in a social media application or an e-commerce recommendation engine or something like that. You will have several hundred models, several dozen, several hundred models that you have to keep track of all of them. And you only have so many data scientists on staff. You can't just keep track of each and every one. And then the other thing that happens is you have your data itself shifts frequently, and you will have to reevaluate the performance of your models in a constant fashion. So these are all reasons why the previous approach that I just showed in the previous slide, it does not scale. So what does it take for it to scale? Well, a state-of-the-art approach now in 2021 looks something like this. So you'll have the actual experimentation, but we now talk about orchestrated experimentation. So you don't have to go through those steps manually. Whenever you want to run a model, a new experiment, you just go in, tweak the specifics of the model for that particular experiment, but otherwise everything else is reproducible. So that's the orchestrated experimentation. It makes the experimentation process much more efficient. And then the next step is, well, you're happy with the model, but what about the software aspects of this? Does this model scale well? Are there changes to the model that means that it might not scale as well as the previous models? Are there changes to the code that mean that this model is not compatible with the systems the way the previous model was? So that's the CI/CD, the continuous improvement and continuous delivery part. And then finally, there's the continuous training that takes into account that even if you're happy with that model in general, like that modeling approach, you're still going to have to refresh the model parameters, the individual parameters of the model on a relatively frequent basis. It can be weekly, it can be sometimes even daily, because you have new data coming in. So this is continuous retraining. I'll talk a little bit more about continuous retraining later to give a more comprehensive example. So this diagram here is a little bit hard to grasp. I mean, it's not hard to grasp, but it's a little bit dense. So I'll try to go through a different angle on the same process. If we look at this diagram here, the first part here in the top left is what people think of as data science and machine learning. This here is where most data science teams are. Now, how do they go to this? They go to the second part, which is the training pipeline and the CI/CD pipeline, where that's now the software development part. And then the continuous training is where they're constantly refreshing their models now based on updates to the data. So this can be automated. You don't want a data scientist to go and like, oh, I have to update the model weights every week because my demand patterns are constantly shifting, or my customer behavior is constantly shifting, or something like that. You can automate that part and leave the more advanced experimentation to the human data scientist. And then finally, there's the serving, like the scaling aspect of it. How many compute nodes do I need at any given point in time to be able to generate predictions, and then monitoring and sending the feedback to the data store and the feature store so that the continuous experiments are possible without having to like have a data engineer be involved every single time. And then all of this is tied together by the feature store, which I just talked about. And then the ML metadata and artifacts are where you're tracking, like, okay, you have 4 different models running in production. Each model has its own set of input features. Each model has its own set of pre-processing transformations. So when you start dealing with a very large number of models, you want to be able to track that. And that's what the ML metadata and artifacts are for. So how does this tie into the business side of MLOps? So let's look at one example. A first example, again, I keep falling back on my past role as a demand forecasting specialist, a demand forecasting pipeline. We have the business will do the forecast setup. So this is in a retail context, and the purpose is to ingest historical sales and inventory data, run it into a forecasting engine, which will have a set of different forecasting algorithms, generate forecasts. Those forecasts are reviewed, and then from once those forecasts are reviewed and approved by an analyst, then the downstream systems will take those forecasts and generate inventory allocations, purchase orders to suppliers, decisions on which stores or which zip codes to send the data to send the inventory to, not the data, sorry, the inventory to. So what does this process look like? Whenever we have a new product, we'll do the forecast setup. So we'll set all of the product attributes, its brand, description, size, volume, flavor, if it's a food product, color, if it's a fashion item, and things like that. The life cycle parameter, so when should we start forecasting for that product, and when will we end forecasting for that product, because we'll be phasing it out and replacing it with a new one. Location attributes, so zip code, which part of the country do we want to send it to, things like that. And finally, whatever monitoring, so whatever thresholds for this product, if it's really important, then we want to make sure that the accuracy is always above X%. We always want to ensure certain availability for certain items, things like that. So we set up these for each individual product. Now we ingest the historical sales and inventory data. These go into a forecast model, which generate the forecasts. The output of that are point forecasts, which is what are the most likely sales values, along with measures of the uncertainty on the forecast. This is fed to a system. We will have a tracking and alerting mechanism that is monitoring the forecasts continuously. And as every time that a forecast starts deviating too much from the ground truth, a analyst is, or either a forecast starts deviating too much from the ground truth, or alternatively, the forecast hasn't deviated too much from the ground truth, but the uncertainty measure on it is really wide. And so those are two situations in which we'd want to review to alert a forecast analyst, hey, don't trust the machine on this one. You probably want to look at it and see what's really happening. The forecast analyst will then look at it. If he likes the forecast, then he'll approve them. Otherwise, he might adjust the forecast up or down, saying, no, I don't think we're going to sell 100 cartons of milk. I think we're going to sell 120. Or the algorithm is overshooting. Actually, I think we're only going to sell 75. So he adjusts the forecast. So they adjust the forecast down to 75. Now, ideally, this is not happening for every single forecast. This is happening for only a small percentage of your forecast. Then those forecasts are fed to the downstream system. So let's consider now what happens when a forecast goes off the rails. Did that forecast go off the rails because there's an actual change in the demand pattern? Something happened and suddenly nobody wants to drink milk anymore, and therefore your forecasts for milk are going to be completely wrong? Or was there something wrong with your data? Was there something wrong with your forecast setup? Was there something wrong with the forecast engine and it started giving bad forecasts? Was it so? This is now where there is a clear difference between MLOps and DevOps. From a DevOps perspective, the only thing we can really look at is the forecast engine. The forecast engine is a piece of software, and if we have all sorts of best practices for managing software in production. We can look at the logs, we can identify if there are any errors or warnings, are there any bugs in the code, and look at and understand from that if the software is giving us bad forecasts or not. However, the software in the forecast engine can be perfectly fine. There are no bugs, no errors. It's running exactly as designed, and it can still give you bad forecasts. Why can that happen? Well, the forecast setup can be wrong, or the historical sales and inventory can be wrong, or neither of the setup is wrong, nor the historical sales and inventory. Everything is fine, but there was a real change in demand patterns. So some influencer went on Instagram and said, you know what, milk is bad for you. Everybody's lactose intolerant. They just don't realize it, and therefore stop drinking milk. People actually believe that, and before you know it, nobody wants to buy milk anymore. So which one of these possible 4 scenarios? Bad software, bad data setup, bad historical data, or real-world change in demand patterns? DevOps allows us to solve for the first case. For the 3 other cases, you have to shift from a software-centric point of view, a code-centric point of view, to a data and model-centric point of view. You have to start thinking, applying the same principles that we learned over the years from DevOps. Now you have to start applying them to the data and the model as well. And you have to bring your business stakeholders into that process in order to be able to do that. If you have nothing but engineers and data scientists on your forecasting team, then you will not be able to apply fully this data-centric and model-centric view, because they don't know enough about the business side of demand and inventory to be able to tell you what's really going on. So this is here, like, demand forecasting gives one very good explanation of why MLOps is just as important to business stakeholders and why the business stakeholders need to be involved in the MLOps process. I'm now going to go to an even more extreme case. Fraud detection. In fraud detection, you have data that is shifting far more frequently than in the demand forecasting case. Why? Because fraudsters are human agents who are intelligent. They sometimes can be pretty advanced ML engineers or data scientists themselves, and they will be trying to second guess whatever you're doing to detect fraud and adapting accordingly. So if they realize that you have been using the IP address of an incoming transaction as a way to identify whether something was a real transaction or fraudulent transaction, they're going to pick up on that immediately. The moment their attempt at fraud fails, they're going to intelligently adapt. And as a result, fraud detection models, which come under 2 types of models, either anomaly detection models or classification models, tend to, the model goes stale very quickly. Every 3-4 weeks, you have to replace new models. So this leads to 2 things. Your data is constantly shifting. The review process unlike the forecasting case where the review process is going to happen on only a minority of the predictions, for a fraud detection use case, anytime the model, the system says this is a likely fraudulent transaction, you want to have it reviewed by either a security analyst or a data scientist, or ideally a data scientist who's also well versed in security as well. And so, like I said, now constantly shifting data, continuous human intervention and review of the predictions, and also as a result, the models are being updated. You're doing new experiments on new types of models almost every week, deciding, you're spending on any given point in time, half of your week is experimenting with new models, and the other half is reviewing security alerts and things like that. So this is another situation where MLOps becomes really, really important, because it is essentially impossible to do efficient fraud detection without having a solid MLOps framework in place. There is one last very important, not one last, but one other very, very important aspect of MLOps from a business perspective, which is being able to explain your predictions. And why would you want to explain your predictions? Well, I mean, it's obvious that you'd want to be able to explain the predictions, but what are the business contexts for being able to explain predictions? Well, I mentioned earlier that you will have a lot of business stakeholders, such as the demand and inventory analysts, or the security analysts in the fraud detection case, or in any, or financial analysts in a financial, a FinServ, a financial services context, or any business situation where you're using AI or ML. Some of the business stakeholders will not be technical, yet they still need to be able to understand why an advanced deep learning model or an advanced XGBoost model is making predictions and how it is doing so. So you want to explain the predictions after the fact. Beyond just being able to explain it to business stakeholders, there are also deeper reasons why you want to do so. You want to be able to confirm. In some situations, there will be regulatory considerations. So if you're using ML models in the medical field, if you're using ML models in financial services or in the real estate mortgage space or something like that, there are regulatory considerations to take in mind, and you have to be able to explain your models in order to meet those, and to explain your models and then modify them accordingly in order to meet those regulatory considerations. For example, if you have a model that predicts a likelihood to default on a loan, you want to make sure that that model falls within whatever regulatory frameworks happen with loans and mortgages and so on. So even deeper than the regulatory framework, there's the ethics framework. AIs and ML models are only as good as the data and the humans who train them. And unfortunately, we still have a lot of bias involved in our data and in our processes. And in order to be able to remove the bias, we would have to, the first step in being able to remove bias from a model is to be able to understand why a model is making prediction. So for example, if we have, let's say there's a use case, a famous use case where a company developed a set of ML models based on cameras that would detect whether whether there was going to be likelihood for increased police presence at a given location. And that model was trained, it was evaluated, it gave pretty good predictions, and then they went and they deployed it in real world scenarios, and they discovered that, lo and behold, the model was giving a lot of false positives. It was far too often alerting the police and saying we need increased police presence in a given location, even though there was no real reason for that. And after the fact, they discovered that when they trained the models, they trained them on certain neighborhoods, and when they deployed them in other neighborhoods. And as a result, that model had not taken into account that there was a complete shift in the feature set and a complete shift in the data from one neighborhood to the other. So that's a situation where, like, there are deep ethical reasons why you need to be able to explain and understand your models in order to avoid pitfalls like the one I just described. So now, to summarize, the AI ethics point of view AI ethics point of view is one reason for why models are really important. Why explainable AI is really important. There are regulatory reasons as well, and finally, you have to be able to explain those models to your business stakeholders. All of this falls into the larger context of the business perspective on MLOps, in the sense that you cannot have a fully mature MLOps practice without involving the business stakeholders and the human stakeholders involved in any prediction effort. Okay. A few points to ponder on where MLOps is going to go, again, from a business perspective. I was watching a talk given by Andrew Ng, who's one of the main contributors and most important figures now in AI and ML. He is the founder of Coursera. He has given some of the best courses in machine learning on Coursera, part of deeplearning.ai. His course on Stanford is one of the go-to courses for machine learning. And during a talk he gave recently, a few weeks back, on MLOps, called From Model-Centric to Data-Centric AI, he opined that MLOps will eventually become verticalized. What does that mean? That means MLOps will not remain a unified discipline applicable across multiple industries and specialties. That there will be, there'll be a special MLOps for inventory and demand forecasting. There will be a completely different type of MLOps for fraud detection, and there will be yet another MLOps for people who are working in the medical industry, and it'll become it will break up into a whole bunch of separate disciplines. That hit really too close to home for me, because as I was studying MLOps over the last 2 or 3 years, I had realized only recently, actually a few weeks before I attended Andrew Ng's talks, that a lot of the stuff that was the day in, day out of an engineering team that's responsible for retail merchandising and demand forecasting pipeline was effectively MLOps. But we didn't call it MLOps, we called it DevOps, or we called it MerchOps. And the reason we did so was that the tool set was radically different. It was based on highly specialized demand forecasting and inventory planning tools. Typically, they were proprietary. They were not open source. Typically, they were on premises. They were not cloud-based. And the terminology and the jargon was very different, but the mindset was exactly the mindset that an ML ops team should have. And so the fact that we didn't call it ML ops because it used such a highly specific technical stack, tech stack, and highly specific terminology and highly specific jargon was the reason why people didn't think of it as ML ops. But then you flip that proposition on its head. Should we be thinking about it as MLOps at all, given just how specific that tech stack and that terminology and those considerations are? And so that's where Andrew Ng's comment hit really, really close to home, because maybe he's right. Maybe we're never going to be able to have like one general MLOps discipline across everything. But then I think about it, no. We shouldn't limit ourselves. That maybe it might be like immediate and the efficient in the short term to just like leave. Demand forecasting teams are very comfortable doing it their way, so have demand ops or merch ops or whatever, and fraud detection teams are comfortable with their methods, and it's better to just take the existing tool sets, which are all based on cloud containers, because it's just so much easier to spin up pipelines with cloud containers, and to let each discipline evolve on its own, become verticalized. But we would be a lot poorer for that, because people won't be able to cross learn. Skills won't be transferable. There might be things that a fraud detection team could teach a demand forecasting team. There might be things that a fraud detection team could teach a team that's working in applying ML to the medical field. The regulatory and ethical concerns that a financial or a mortgage related ML ops team knows about could be very well applicable to demand forecasting or to inventory. They're like, why would demand forecasting have any ethical considerations? Well, it might. And we can learn a lot from the people who already have to take into account ethics considerations because they're working in finance or in real estate or in fraud. So I think, an answer to Andrew NG's comment that MLOps will eventually become verticalized, that might be a good idea in the short term. In the long term, I don't think so, and it shouldn't. But predictions about the future, as somebody who works in data science and demand forecasting, are always tenuous, so we'll wait and see. And with that, I would like to say thank you and open it up to questions.
Thanks, Skander. So we do have a good question here in the chat from Indra. With regard to predictions and forecasts, on average, what sources are being considered, especially with reference to the supply chain, in which cultural nuances, environmental, social, and governance goals, and multi-tiered regulatory compliance are all factors?
So for sources of data and demand forecasting considerations, typically the sources used are historical sales and inventory data. That's the first, that's the you can't go anywhere without that data. That's the most basic data source. As a demand forecasting practice matures, people are then become able to include product attributes. So detailed data about the products, if we go to the fashion use case, the color, the size, the brand, eventually even images from that product. That's kind of like the second tier, which a lot of, or even most, I would say, demand forecasting teams are there now. The third tier, which most people are experimenting with, but they haven't yet completely succeeded in incorporating, is signals from social media, signals from geographical data like maps, foot traffic in a store, in a given shopping area, things like that. People are still working on incorporating that. And that is also probably where we start coming up against regulatory considerations and privacy considerations and so on. But so we're kind of it's in flight. We haven't yet figured out completely how to incorporate those in demand forecasting models. Now, in including any regulatory, historically, the best way to include regulatory considerations in a forecast and in a supply chain context has been to apply it after the fact on top of the forecast. So if you're shipping something somewhere, the forecast says you can ship 100 units, but there are reasons why you should only ship 10 or 20. That is a business rule that's applied by the inventory system after the fact on top of the forecast. To your point, however, the problem is becoming increasingly complex, especially with the additional data signals and data sources that are being included. And we do have to start thinking about that at the source of the data, not applying it after the fact. And that's where AI explainability comes in. Google has just replaced open sourced a model last year called temporal fusion transformers, which provides explainable forecasts. That is a first step, but it's very much still a first step. There's a lot of work to be done. Thank you. That was a really great question.
I don't see any other questions in chat. We've got some great comments from Karen. And Karen, you might want to connect with Skander in the networking breakout space. I actually have a question for you, just based on experience. When you had to think of a really successful engagement with a business team, were there specific factors, whether they were part of the overall training, proficiency, literacy afforded to the team inside of Google or Nordstrom, or just maybe something about the profile of the team members? Where did you see a lot of really strong engagement from business?
I think the most successful efforts have always been when engineering and business were really close. So when engineering and data science, and so there's actually an implicit question in your question there, which is, first of all, in some places I've been, data science were part of engineering. So they were considered a technical skill, and therefore they were, one particular role and track or skill within an engineering team. In other situations, data science was a separate organization altogether. And in yet a third category of company or I shouldn't say company, a third approach has been to have the data scientist part of the business, right? In any situation, however, the most successful efforts and the fruitful results and where, like, using ML models in general and using MLOps tools in particular was the most successful has been when the business stakeholder is really close to the scientist and the engineer. When the business stakeholder sits in a separate building and only interacts with the scientist and the engineer in a formal context of, let's meet once a week and kind of review results, and let's exchange like send stuff over email, that hasn't really led to good results.
Right.
When the business stakeholder is really close to the engineer and the data scientist, if they are working in person, they are very close together. They are on the same floor or even sitting in the same cubicle pod or the same general area of the building. Or if they're working remotely, they are comfortable enough that they can Slack each other or whatever, like, chat tool is being used by their organization on a constant basis and interact informally as frequently as possible, and are comfortable enough to tell each other up front that this idea is good or this idea is bad, that this modeling approach is good or this modeling approach is bad, then that's when they get successful results. To give you an example, when I was working as a data scientist at Nordstrom, and I went down the path of trying to generate forecasts for items that were really, really slow movers. What's a slow moving item? When you have like a very high end suit or a very high end piece of jewelry or something like that, it might sell once every 6 months. And I went down the path of trying to use improved machine learning to forecast that. And there was a whole bunch of literature, research papers were written on the topic. The academics were proposing all sorts of methods how to do that. The business stakeholder told me, no, don't. That's a stupid idea. Stop doing that, because the way we order those from suppliers is such that we don't need to forecast them at all. Now, she could tell me to my face that I was stupid and that I shouldn't be doing that because we were comfortable and we had a really good relationship. But if this had been a formal situation where we were meeting like very formally in official meetings, and it was like this exercise that happened every week or every 2 weeks with managers present, she wouldn't be able to be as blunt and as forthcoming. And I probably would have spent 3 or 4 months developing models to try to forecast those items before it finally turned out that they were useless. So it's that level of comfort is necessary, and I know that it's challenging now with everybody working remotely, but you have to have that in order for machine learning and ML ops projects to succeed.
That's helpful. Let's try to, we got about 1 minute left and we did get a question just in, so let's try to sneak this in. Given the complexities that are associated with MLOps, would you elaborate on the skill set gap to include where academia may be dropping the ball?
I think where academia is dropping the ball is in teaching people how to teaching data scientists how to incorporate tribal knowledge. From, like, the example that I just mentioned is actually an answer. It's not a high level answer, but it's an example of the type of thing that you're never going to get in academia.
Right.
And so the soft skills, teaching data scientists to listen more to business stakeholders, to realize that math is not the solution to everything, and to know that there's like this tribal knowledge, this accrued wisdom in the business that is just as valuable as any modeling effort. That's the thing that academia probably needs to put a little bit more emphasis on than it has up until now.
Okay, great. With that, I think we're about to close here. So want to thank you again, and thanks everybody for participating. Skander, you'll be around in the networking room later, I believe,
Yes.
if people want to chat some more.
Okay.
Okay, thanks so much.
Thanks.
Bye-bye, everybody.